we have to prove this, right. So, imagine this, right. So, rough proof sketch. Okay. So, how does this go? So, I know this. What is limit t tending to infinity mij of t over t. Remember that mij of t, which is the renewal, it is a delayed renewal process counting the number of returns to j by time t. This will be equal to 1 over w bar of j almost surely, right. This is just strong law for delayed renewal processes, right. So, this I know. What else do I know? So, this is one. Okay. If I look at limit t tending to infinity mij of t over mi of t. Okay. So, mij of t is the number of returns to j until time t, mi of t is the number of transition made by the process until time t. Now, this also has a limit. Okay. Let us see what it is. Okay. I am going to write this as nij of mi of t over mi of t. This can be shown, all right, limit t tending to infinity. Now, what is this nij? Ni of j, nij of n is equal to number of returns to state j till n transitions in the embedded DTMC. So, the embedded DTMC keeps making transition, and I am going to say that Nij of n is the so given x not equal to I. Given that I start at I, what is the number of times I return to j until there are n transitions in the embedded Markov chain. Okay. Now, until time t, there are mi of t transitions in the CTMC, which corresponds to Nij of mi of t transitions to state j, right, in the DTMC. Is that clear? So, if you look at this guy, so now remember that this argument, this guy goes to infinity as t tends to infinity, that we have already shown. So, this is like limit n tending to infinity Nij of n over n, correct. Now, what is limit n tending to infinity Nij of n over n? It is simply the fraction of transitions that go into state j in the embedded DTMC, and that we know is equal to pi j almost surely, correct. So, that is very nice then, right. So, this is number 2, right. So, what does, if you put these two together, what do we get? From so 1 and 2, I can get something, right. So, I can get 1 over w bar of j is equal to limit t tends to infinity mij of t over t, which is simply limit t tends to infinity mij of t over mi of t times mi of t over t, right. That is simply pi j times limit t tending to infinity mi of t over t, correct. All of this holds almost surely. Therefore, what does this say, right? It says that limit t tends to infinity mi of t over t is almost surely equal to 1 over pi j w bar of j, right. So, what have we shown, right? In this calculation we have shown that there is such thing as a average rate at which transitions happen in the CTMC, right. So, that there is an almost sure limit to MIT over T, right, and that is equal to 1 over pi j wj bar. So, this also means that 1 over pi j wj bar is constant across all the states, right. So, this 1 over pi j wj bar has to be equal to 1 over pi k wk bar, all of this will be equal to mi of t over t, right. So, the RHS is independent of, is constant for all j. For all states j, that is the first conclusion. The second conclusion is that limit t tends to infinity, mi of t over t exists almost surely. So, these two conclusions follow. Okay. So, this is a nice conclusion. So, now if you go back to the average fraction of time, right, which is Pj, we called it Pj of I and then we got rid of the I dependence, right. Pj of I, which is we are just calling it Pj, is equal to 1 over nu j w bar of j, correct. So, which is equal to, if you bring this up, this will be equal to pi j over nu j limit t tends to infinity mi of t over t, almost surely, right. So, this guy is just a constant, which is 1 over pi j w j bar. We know that it is constant and is independent of any state j, right. So, what we have shown is that Pj is just proportional to pi j over nu j, right, and there is a multiplying constant which is the limit of the rate at which the transitions happen, correct. Now, so if you were naively were to think about it, you would say that, so basically, right, naively, so Pj is proportional to pi j over nu j, right, and there is a constant in front which is that limit. So, if you were to normalize, so this is the Pj is the fraction of time spent in some state j, right, and the CTMC has to be in some state or the other, right. So, you might argue, if you were to be naive about it, normalize and say that Pj should be equal to pi j over nu j over sum over pi j over nu j, sum over let us say pi k over nu k, which is sort of the answer we want, right. Well, this answer is correct, but to show this properly requires some amount of work, okay. Also you need that the denominator should be finite, this guy should be finite, right, otherwise you will not get a probability distribution at all, okay. So, this is naively is, you can put this in a bracket, right. To show this more properly, you have to again use some renewal arguments, okay. I am going to give a reward. So, I am going to say, I am going to look at a truncated reward, okay, Rijl of t equal to 1, okay, whenever x of t is less than or equal to L, okay, and this is a reward process. So, consider this reward process for the linear renewal process mij of t. Okay. So, I am going to give a reward of 1 whenever my state is anything from 1 to L or 0 to L, alright. So, for this what happens, right. So, the fraction of time spent in anywhere from 0 to L, which is simply Pj j equals 1 to, I am applying renewal reward now, right, j equals 1 to L, Pj is equal to expected Rijl, which is the expected reward per renewal interval divided by the expected width of the renewal interval, which is W bar j, correct. Now, what is the, now I want to really show that this Pj's in fact sum to 1, right, the fraction of time spent in state j Pj, when I sum over all states I want to show that that's equal to 1, right. It's sort of intuitively reasonable, but I am trying to show this rigorously, that is what I am trying to prove, right. Now, I want to show, so this is correct, right, this is almost surely true by renewal reward theorem. I am going to send L to infinity now, right. Now, if I send L to infinity, what happens? I have to send, this is true for all L greater than or equal to 1, okay. Limit L tends to infinity, sum over j equals 1 to L, Pj is equal to limit L tends to infinity, the denominator has no L, only the numerator has L, expected Rijl over W bar j. See, if you look at this now, you have to show that the limit of the numerator is in fact equal to W bar j, okay, because you want to show that sum over Pj L j is equal to 1 to L, L tend to infinity is equal to 1, right. So, if you look at this, if you just look at, maybe I should draw a picture here, this is time 0, right. So, you are hitting j here, let us say j here and all that, okay, and whenever your state is less than or equal to L, you get a reward of 1, okay. So, if you have L minus 1 or 1 or 2 or whatever, you get a reward of 1, okay. So, I am saying that you get a, so this reward is 1 whenever your state is less than or equal to L, 0 otherwise, okay. Now, as L tends to infinity, what happens, right? If you look at this Rijl, right, Rijl has two properties. See, it is clearly monotonic in L, right. Rijl as a random variable is monotonic in L, and as L tends to infinity, as L becomes larger and larger, Rij of L basically approaches Wjj, which is the width of the interval, right. And because of the monotonicity, we can invoke monotone convergence theorem and argue that by monotone convergence theorem, we can argue that, see, Rijl monotonically increases to Wjj, therefore, expectation of Rijl approaches expectation of Wjj, which is W bar of j. Monotone convergence theorem. So, this is the technical step, okay. So, what is intuitively reasonable is taken care of by the famous monotone convergence theorem, is therefore, this is W bar of j. This implies sum over j equals 1 to infinity, Pj equals 1, right, where Pj is the time average fraction of time spent in state j, right. So, you can truly normalize and get that answer that you always wanted, right, and then you can go back, plug it back, since Pj is known to be, so this Pj is now known, right, in this equation, you can get the value of that, right, as equal to being equal to whatever the theorem states right here, right, and Wj bar you can also substitute, where is Wj bar? So, you know Pj and nu j, right. So, you know Pj, you know nu j. So, you can get Wj bar in terms of the pi's and nus, and you can get that, alright. So, that concludes the theorem. So, bottom line is that we have shown the pk, the fraction of time spent in state j, which is also the steady state probability of state j, is given by that equation. The expected renewal duration is given by that equation, and the expected rates of transition is given by this equation, alright. We will stop here.